Imagine yourself floating in space, looking out at the vast universe. Around you, the galaxies are not still. They are like islands of light on an ocean of space that is constantly expanding, drifting further and further apart at an unimaginable speed. This is one of the greatest and most fundamental discoveries of the 20th century, confirmed by the astronomer Edwin Hubble. It tells us that our universe has a history, a beginning. We know the universe is expanding, but a seemingly simple question is now causing a headache for the world's best cosmologists. How fast is it expanding? And here is the strange part, the part that has created one of the most silent but profound crises in modern physics. When we try to measure that speed using our most reliable methods, we get two different answers. Not just slightly different, but systematically and inexplicably different. It is like looking at the speedometer of a car and seeing it read 60 kilometers per hour, but at the same time, a radar gun on the side of the road clocks it at 65 kilometers per hour. Both instruments are built with the highest precision, so why don't they agree? Where is the error? In the car, in the radar gun, or in our very understanding of the laws of motion? This is the Hubble tension. Welcome back to Science for Sleep. If this journey into one of the greatest mysteries of modern physics sparks your curiosity, a gentle tap of the like and subscribe buttons will help us continue these investigations together. And as always, I would love to know where you are listening from. Please feel free to leave a greeting in the comments so we know how far this story has traveled. In tonight's video, we will become cosmic detectives. We will examine two different crime scenes. One is the echo from the Big Bang itself, and the other is the light from dying stars much closer to us. We will learn why they tell two different stories about the same universe, and whether this paradox might be pointing the way to a completely new kind of physics. Let us begin. To understand the first piece of this cosmic puzzle, we must begin our investigation not in the present, but in the deep, distant past. The universe provides us with a remarkable kind of time machine. Because light travels at a finite speed, when we look out at distant objects, we are not seeing them as they are now, but as they were when the light first left them. Looking at the Andromeda galaxy, we see it as it was 2.5 million years ago. Looking at more distant galaxies, we are peering billions of years into the past. And if we look far enough, with the right kind of instrument, we can see all the way back to the echo of creation itself. This is the first of our two crime scenes. It is known as the Cosmic Microwave Background, or CMB. The story of its discovery is one of serendipity. In 1965, two American radio astronomers, Arno Penzias and Robert Wilson, were using a large horn antenna in New Jersey to study radio waves from the Milky Way. They were plagued by a persistent, faint, and uniform hiss in their signal, a noise that came from every direction in the sky, day and night, no matter where they pointed the antenna. They tried everything to eliminate it. They recalibrated their instruments, checked their connections, and even famously cleaned out the pigeon droppings that had accumulated inside the antenna, thinking it might be the source of the interference. But the hiss remained. It was a cosmic signal, a whisper from the universe itself. Unbeknownst to them, just a few miles away at Princeton University, a team of theoretical physicists had predicted the existence of this very signal. They realized that if the universe had begun in a hot, dense state, as the Big Bang theory proposed, then the leftover heat from that initial fireball should still be detectable today, cooled and stretched by billions of years of cosmic expansion into a faint microwave glow. When Penzias and Wilson learned of this, they understood. They had not found noise, they had found the oldest light in the universe. This light, the CMB, is effectively the baby photo of our cosmos, a portrait taken when the universe was just 380 years old. Before this time, the universe was an opaque, glowing fog. It was so hot and dense that light particles, photons, could not travel freely. They were constantly bouncing off a thick soup of free-flying electrons and protons, trapped in an endless game of cosmic pinball. But as the universe expanded, it cooled. And at 380 years, it reached a critical temperature. It became cool enough for electrons and protons to finally combine and form the first stable, neutral hydrogen atoms. This event, known as recombination, was a turning point. With the free electrons now bound up in atoms, the universe suddenly became transparent. The photons were free, released from their pinball game, and they began to stream across the cosmos, unimpeded, for the first time. The light that we detect today as the CMB is that very first light, a snapshot of the universe at the exact moment it became transparent. Having traveled for 13.8 billion years, its wavelength has been stretched by the expansion of space from high-energy light into the cool, low-energy microwave part of the spectrum. When we create a map of the CMB, we are looking at a picture of the infant universe, and this picture contains a remarkable amount of information. It is like a cosmic genetic code, a blueprint that holds the precise ingredients of the early universe, the exact amounts of ordinary matter, dark matter, and the initial influence of dark energy. It is the starting condition for everything that would follow, the seed from which every star and galaxy would eventually grow. The cosmic microwave background provides a stunningly detailed portrait of the infant universe, a blueprint containing all the initial ingredients and conditions. From this single image, a team of cosmic detectives can construct a robust model of how the universe should have evolved over the next 13.8 billion years. This is the first of our two methods for measuring the Hubble constant. It is an indirect measurement, a prediction based on a deep understanding of the laws of physics and the universe's starting point. Using the precise data from the CMB, particularly from missions like the Planck satellite, cosmologists have built what is known as the Standard Model of Cosmology, or lambda CDM. This model is incredibly successful. It takes the ingredients seen in the baby photo, the exact amounts of dark energy, lambda, cold dark matter, CDM, and ordinary matter, and uses Einstein's theory of general relativity to calculate how the universe should have expanded and evolved over time. Think of it like this. If you have the precise recipe and starting temperature of a loaf of bread dough, you can use the laws of chemistry and physics to predict exactly how much it will rise and what its final size will be. In the same way, by knowing the precise recipe of the early universe from the CMB, the lambda CDM model can predict what the expansion rate of the universe should be today. This method, rooted in the physics of the early universe, gives a very precise value for the Hubble constant. It is a prediction based on our most fundamental and successful theory of the cosmos. For a long time, it was assumed that when we finally developed the tools to measure the current expansion rate directly, the number would match this prediction, confirming our elegant model of the universe. But as we shall see, the universe had a surprise in store. Our first method of investigation has taken us back to the dawn of time, to read the secrets of the universe from its baby photo, the cosmic microwave background. This gives us a powerful prediction of how the universe should be behaving today. But a prediction, no matter how elegant, must be tested against direct observation. We must now turn our attention to the second group of cosmic detectives, those who measure the expansion of the universe not by looking at its past, but by looking at its present. This is the second method, a direct measurement of the local universe, the universe of here and now. To do this, astronomers need a special kind of tool. They need a standard candle. Imagine you are in a vast, dark field at night, and you see hundreds of lights scattered across the landscape. Some are bright, some are dim. You cannot tell if the bright ones are powerful lights that are far away or weak lights that are very close. But what if you knew, with absolute certainty, that every single light in the field was a 100-watt light bulb? Then, your job would become simple. The dimmer a light appeared, the farther away it must be. By measuring its apparent brightness, you could calculate its exact distance. This is the principle of a standard candle, an astronomical object with a known, consistent intrinsic brightness. Finding such objects is the key to mapping the true distances in the cosmos. And in the vastness of space, the most reliable and most spectacular standard candles we have ever found are born from the violent death of a star. These are type Ia Supernovae. They are not just any stellar explosion, they are a very specific kind of cataclysm with a remarkably consistent outcome. The story of a type Ia supernova is a slow cosmic drama that unfolds over billions of years, a story of two stars locked in a final fateful embrace. It begins with a binary star system, two stars orbiting each other. One of these stars, similar to our Sun, has already lived out its life. It has burned through its hydrogen fuel, puffed off its outer layers, and all that remains is its small, dense, and incredibly hot core, a white dwarf. A white dwarf is a dying star, no longer generating energy through fusion. It is a cosmic ember, slowly cooling over eons, but its story is not over. Its companion star is still alive, and as it ages, it begins to swell into a red giant. As its outer layers expand, they get close enough for the immense gravity of the white dwarf to begin siphoning off material, primarily hydrogen and helium gas. Like a silent, patient thief in the night, the white dwarf begins to steal matter from its companion. This stolen gas spirals down onto the white dwarf's surface, forming an accretion disk and slowly adding to its mass. For millions of years, this process continues, the white dwarf growing heavier and heavier, its density increasing under the immense gravitational pressure. But there is a limit. An Indian-American astrophysicist named Subramanian Chandrasekhar calculated that a white dwarf cannot grow indefinitely. There is a precise, critical mass, known as the Chandrasekhar limit, which is about 1.44 times the mass of our Sun. If a white dwarf ever exceeds this limit, its internal structure can no longer withstand the force of its own gravity, and it begins to collapse. This collapse triggers a runaway thermonuclear reaction. In a fraction of a second, the carbon and oxygen in the white dwarf's core fuse into heavier elements all at once. The result is a cataclysmic explosion that completely obliterates the star. This is a type Ia supernova. And because every single one of these explosions is triggered by a white dwarf reaching the exact same critical mass, the energy they release is astonishingly uniform. They all explode with virtually the same intrinsic brightness. They are perfect standard candles, cosmic lighthouses that shine with a known, reliable wattage across the universe. When astronomers spot one of these explosions in a distant galaxy, they can measure how bright it appears, and because they know how bright it truly is, they can calculate the distance to that galaxy with incredible precision. These dying stars are the rulers on our cosmic map, the reliable beacons that allow us to measure the vast, dark distances of the here and now. With these perfect, cosmic lighthouses now identified, the second team of detectives can begin their work. Their method is direct, empirical, and incredibly challenging. They do not look back to the universe's infant portrait. Instead, they meticulously survey the local universe, the vast expanse of galaxies around us, searching for the fleeting, brilliant flashes of these dying stars to build a map of the cosmos, one explosion at a time. This great undertaking has been led for decades by astronomers like Adam Rees, a Nobel laureate, and his teams, using our most powerful eye on the universe, the Hubble Space Telescope. The work is a testament to cosmic patience. Astronomers point Hubble at distant galaxies and watch, taking picture after picture, waiting for a new star to appear where there was none before. When they catch one, a new type Ia Supernova, the race against time begins. These explosions fade quickly, so they must measure its peak apparent brightness with extreme precision. The dimmer the explosion appears, the farther away it must be. But to turn this apparent brightness into a precise distance, they need a ruler. This is where a crucial tool called the cosmic distance ladder comes into play. It is a series of overlapping measurements that allows astronomers to calibrate distances from our own galactic neighborhood out to the farthest reaches of the cosmos. The first rung on this ladder involves measuring the distance to nearby stars in our own galaxy using parallax, a method similar to how our own two eyes perceive depth. The second rung uses this knowledge to calibrate the brightness of another kind of star, the Cepheid variables. These are pulsating stars whose true brightness is directly related to the rhythm of their pulsations. By finding Cepheids in nearby galaxies, astronomers can determine the distance to those galaxies, and the final, crucial step is to find galaxies that contain both Cepheid variables and a recent type Ia supernova. By using the Cepheids to calculate a precise distance to that galaxy, they can then calibrate the exact intrinsic brightness of the supernova itself. With this cosmic ruler now calibrated, the team can look at supernovae in even more distant galaxies and, by measuring their brightness, confidently determine their distance from us. Once they know the distance to a galaxy, the final step is to measure its speed. They do this by analyzing the galaxy's light, looking for redshift. As the universe expands, it stretches the wavelength of light traveling through it, shifting it towards the red end of the spectrum. The greater the redshift, the faster the galaxy is moving away from us. By combining the precise distance measured from the supernova with the precise speed measured from the redshift, astronomers can directly calculate the current rate of the universe's expansion. This method, a direct observation of the universe in motion today, also yields a very precise value for the Hubble constant. And for a long time, the expectation was that this number, born from the light of dying stars in the present, would perfectly match the number predicted from the echoes of the Big Bang in the past, beautifully confirming our entire understanding of the cosmos. But it did not. And so, we now have two independent, powerful, and remarkably precise methods for measuring the expansion of the universe. The first method looks at the ancient light from the cosmic microwave background, the baby photo of the universe, and uses our best theory of cosmology, the lambda CDM model, to predict what the expansion rate should be today. The second method looks at the local universe, using the brilliant, fleeting light of type Ia Supernovae as standard candles to directly measure the expansion rate as it is happening now. For decades, as the precision of these measurements improved, the entire world of cosmology expected these two numbers to converge, to meet at a single, beautiful value that would confirm our elegant understanding of the universe. But they did not. Instead, as the error bars on the measurements shrank, a stubborn and undeniable discrepancy emerged. The two methods give two different answers. The measurement from the early universe, based on the CMB and the Standard Model, predicts a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The measurement from the local universe, based on supernovae and the cosmic distance ladder, yields a value that is consistently higher, around 73 or 74. This might not sound like a huge difference, but in the world of precision cosmology, it is a gaping chasm. The error bars on both measurements are now so small that the chance of this being a statistical fluke is less than 1 in a million. The discrepancy is real, it is persistent, and it suggests that there is something fundamentally wrong, or at least incomplete, with our standard model of cosmology. This is the Hubble tension. It is not a loud, explosive crisis, but a quiet, deep, and profound one. It is a crack, appearing in the very foundation of our understanding of the universe. It is like two trusted detectives investigating the same case, using different but equally reliable methods, and arriving at two completely different conclusions. The data from one tells us one story, and the data from the other tells us another. The inescapable conclusion is that there must be a missing piece of the puzzle, a secret witness, a new physical law, or an unknown ingredient in the cosmic recipe that we have not yet accounted for. The tension between these two numbers is the most exciting mystery in modern cosmology, a clue that points the way toward a new, deeper understanding of our universe. The discrepancy between the two measurements, one from the early universe and one from the local universe, is the central mystery of the Hubble tension. If it were just one measurement versus another, it might be dismissed as a potential error in a single experiment, but the story is more complex than that. In our cosmic detective case, other witnesses have come forward, and their testimonies complicate the picture beautifully. Scientists have developed other, independent methods to measure the Hubble constant, and intriguingly, these other methods tend to agree with one of the two main camps. Let's first look at other methods that measure the local universe. Instead of using type Ia Supernovae, some astronomers use a different kind of celestial beacon, the light from distant quasars that has been bent by the gravity of a massive galaxy in front of it. This phenomenon, known as gravitational lensing, creates multiple images of the same quasar. Because the light from each image travels a slightly different path through the warped spacetime around the galaxy, the images flicker at different times. By measuring the time delay between these flickers and knowing the geometry of the lensing galaxy, astronomers can make a completely independent calculation of the Hubble constant. The result from this method consistently aligns with the higher value found using supernovae. Now let's look at another method that measures the early universe. Scientists can study the large-scale structure of the cosmos, the vast web of galaxy clusters and voids. In the early universe, sound waves rippled through the hot plasma, creating a characteristic pattern of density fluctuations. This pattern, known as baryon acoustic oscillations, became frozen into the universe's structure when it cooled. By measuring the size of these fossilized sound waves in the distribution of galaxies today, scientists can determine how much the universe has expanded. This method, rooted in the physics of the early cosmos, consistently yields a result that agrees with the lower value predicted by the cosmic microwave background. So, we have a clear division. The methods that measure our universe today consistently give us a faster expansion rate. The methods that rely on our model of the early universe consistently give us a slower expansion rate. This is no longer a simple disagreement between two experiments. It is a deep and systematic conflict between our understanding of the universe's past and our observation of its present. The detectives have cross-examined all the witnesses, and their stories do not align. This strongly suggests that the problem is not with the measurements themselves, but with the theory that connects them, our standard model of cosmology. There must be a missing ingredient, a hidden chapter in the story of the cosmos that we have not yet read. The growing tension between our two most trusted cosmic measurements leaves us at a profound and exciting crossroads. It strongly suggests that our standard model of cosmology, while incredibly successful, is missing a key ingredient, or that there is a fundamental flaw in our understanding of the universe's timeline. This discrepancy is a clue, a breadcrumb trail leading us toward a new, deeper physics. Let us now, like cosmic detectives, examine the leading suspects, the theoretical possibilities that could resolve this beautiful crisis. The first and most popular suspect is a change in the nature of dark energy. In our standard model, dark energy is represented by Einstein's cosmological constant, a simple, unchanging energy inherent to the vacuum of space itself. But what if dark energy is not constant? What if it is dynamic? Some theories propose a new form of energy, sometimes called early dark energy, that was present only in the infant universe. This early dark energy would have given the cosmos an extra push shortly after the Big Bang, altering the expansion rate in a way that our standard model doesn't account for. This would change the calculations based on the cosmic microwave background, potentially bringing them into alignment with the measurements from the local universe. Another possibility involves dark matter. Our standard model assumes that dark matter is cold, meaning it moves slowly and interacts only through gravity. But what if dark matter is more complex? Perhaps a portion of dark matter has some small, undiscovered interaction with normal matter or radiation. This interaction would have slightly altered the conditions in the early universe, affecting the patterns in the cosmic microwave background and, once again, changing our prediction for the Hubble constant today. A third suspect is a new, undiscovered particle. Our universe is already filled with ghostly neutrinos. Some physicists propose the existence of a new type of sterile neutrino or other dark radiation that would have been present in the early universe. These particles would have contributed to the total energy density of the cosmos, speeding up its expansion in its youth. Adding this new ingredient to our cosmological recipe could potentially resolve the tension between our two measurements. Each of these possibilities would require a significant revision of our standard model of cosmology. They all point to a richer, more complex universe than we had imagined. The Hubble tension is not a failure. It is a discovery in waiting, a puzzle that is forcing us to look beyond our current understanding and search for the new physics that will define the next era of cosmology. The first suspect in our cosmic investigation, early dark energy, proposes a change to the very engine of cosmic expansion. But our second suspect suggests a different kind of plot twist. What if the problem lies not with the expansion itself, but with the invisible matter that gives the universe its structure? What if dark matter is not as simple or as dark as we have long assumed? In our standard model of cosmology, dark matter plays a simple but crucial role. It is the invisible scaffold of the cosmos, the great, silent mass that holds galaxies and galaxy clusters together with its immense gravitational pull. We call it cold because we assume it moves slowly, and we call it dark because we assume it interacts only through gravity, remaining completely aloof from the world of light and ordinary matter. It is the universe's quiet, gravitational anchor. But what if this assumption is wrong? What if dark matter is not completely isolated? Some theories propose that there might be a subtle, undiscovered interaction between dark matter and the other components of the universe, like radiation or normal matter. This interaction would be incredibly weak, far too faint to be detected in our modern universe, but it could have been significant in the extreme heat and density of the early cosmos, right after the Big Bang. If dark matter could interact, even slightly, with the hot plasma of photons and particles in the early universe, it would have changed the physics of that era. This interaction would have acted as a slight drag, slowing the cooling of the plasma and altering the way sound waves traveled through it. This change, however small, would have left a distinct fingerprint on the cosmic microwave background. The specific pattern of hot and cold spots in the CMB, the very data our early universe team uses to make their predictions, would be subtly different. It would mean that when we use our standard model, which assumes no such interaction, to calculate the Hubble constant, we are starting with slightly incorrect initial conditions. Our prediction would be skewed from the very beginning. By adding a small amount of interaction for dark matter into our cosmological model, we could potentially adjust our prediction of the Hubble constant, bringing the value derived from the early universe up to match the value we observe in the universe today. This idea is deeply compelling because it doesn't require inventing a completely new form of energy. It simply adds a new layer of complexity to a substance, dark matter, that we already know exists but do not yet understand. It suggests that the dark sector of the universe may not be a simple, solitary entity, but could have its own rich and complex physics, its own forces and interactions that we have not yet discovered. The invisible scaffold of the cosmos might not be a simple, inert structure. It could be an active participant in the story of cosmic evolution, its secret interactions in the past now revealing themselves as a profound tension in our measurements of the present. Our investigation into the Hubble tension has led us down two intriguing paths. The first suspect was early dark energy, a new force that might have changed the expansion rate of the infant universe. The second was the possibility of a hidden interaction within the dark matter sector. Now, we turn to our third, and perhaps most elusive suspect, a particle that is already a well-known master of disguise and mystery in the world of physics. This suspect is the neutrino. Neutrinos are fundamental particles, born from the nuclear reactions inside stars, from supernova explosions, and from radioactive decay here on Earth. They are incredibly abundant. Trillions of them are passing through your body every single second. And yet, they are almost undetectable. They have no electric charge, and their mass is so vanishingly small that for a long time, scientists thought they had no mass at all. They interact with other matter only through the weak nuclear force and gravity, making them the ultimate ghosts of the particle world. They can travel through the entire Earth without hitting a single atom. The standard model of particle physics originally, and incorrectly, predicted that neutrinos were massless. The discovery in the 1990s that they do in fact have a tiny mass, and that they can oscillate or change between their three different flavors, electron, muon, and tau's, a Nobel Prize-winning discovery, and one of the first major cracks in the standard model. It proved that our most successful theory of particles was incomplete. This history makes the neutrino a natural suspect in our current cosmic crisis. If we were wrong about them once, perhaps we are still underestimating their role in the universe. The theory related to the Hubble tension suggests the existence of a fourth, hypothetical type of neutrino, known as a sterile neutrino. Unlike the three known flavors, this sterile neutrino would not interact through the weak nuclear force at all. It would be a true ghost, interacting only through gravity. It would be completely invisible to all of our current particle detectors. But if such a particle existed in the early universe, it would still have mass and energy, and therefore it would have contributed to the total energy density of the cosmos. This extra energy would have had a subtle but significant effect on the universe's expansion during its infancy. It would have acted as a form of dark radiation, causing space to expand slightly faster than our standard model predicts. This, in turn, would alter the size of the patterns, the baryon acoustic oscillations, that were frozen into the cosmic microwave background. If the universe expanded faster in its early days due to this hidden particle, then our calculations based on the CMB would need to be adjusted. By adding the effect of this sterile neutrino into the lambda CDM model, it is possible to change the predicted value of the Hubble constant, potentially resolving the tension by bringing the prediction from the early universe into alignment with the measurements from the present day. The idea of a sterile neutrino is compelling, but for now, it remains purely theoretical. Our particle physics experiments have not yet found any definitive evidence for its existence. It is another tantalizing possibility, another whisper of a new physics that may be waiting just beyond the reach of our current instruments, a ghostly solution to a cosmic mystery. We have explored the potential suspects, the theories that could resolve the great cosmic disagreement known as the Hubble Tension. We have considered a dynamic dark energy, an interactive dark matter, and even a new, ghostly sterile neutrino. But there remains one final, and perhaps most humbling, possibility to consider. What if there is no new physics? What if the universe is not more complex than our model suggests, but rather, our measurements of it are? What if the discrepancy lies not in the cosmos, but in ourselves, in some subtle, systematic error in our observations that we have not yet managed to find? This is a possibility that scientists take very seriously. Before declaring a crisis in cosmology and calling for a new theory, the scientific method demands that we first exhaust every possibility of error in our own work. It requires a profound level of self-scrutiny and a willingness to question our most trusted methods. The teams working on the Hubble constant are among the most meticulous and careful researchers in the world. They account for countless variables that could affect their data. For the team measuring the local universe, this means accounting for the dust in our own galaxy and in distant galaxies, which can dim the light from a supernova and make it appear farther away than it is. It means understanding the precise chemistry of each supernova explosion to ensure it is truly a standard candle. And it means building the cosmic distance ladder with incredible precision, a process that involves many overlapping steps, each with its own potential for small, systematic errors to creep in. For the team measuring the early universe, it means creating astonishingly precise maps of the cosmic microwave background, filtering out all the foreground noise from our own galaxy. It means using our understanding of plasma physics and recombination to build the standard model of cosmology, a model that has been stunningly successful in explaining so many other features of the universe. The possibility that both of these meticulous, independent, and multi-decade research efforts have a hidden, systematic error of the same magnitude is considered by many to be very unlikely. And yet, until the tension is resolved, it remains a possibility that must be explored. This scientific humility, this constant questioning of our own results, is not a weakness. It is the very heart of the scientific process. It is what separates science from dogma. It is the engine of progress, the quiet understanding that our knowledge is always incomplete, a map that is constantly being redrawn with every new piece of data, always striving to get closer to a reality that may be far stranger and more beautiful than we can currently imagine. The Hubble tension, this quiet disagreement between two of our most trusted ways of seeing the universe, is not a sign of failure. In the long and beautiful history of science, moments like these crises, are often the most fertile ground for discovery. They are the cracks in the old foundation through which the light of a new understanding begins to shine. They are the precursors to revolution. Over a century ago, physics faced a similar crisis. Newton's elegant laws of gravity, which had worked perfectly for centuries, failed to precisely predict the orbit of the planet Mercury. It was a tiny discrepancy, a small wobble that most would have ignored. But it was a real, persistent anomaly. And that small crack in the old theory was precisely where Albert Einstein's new theory of general relativity took root, a theory that would completely reshape our understanding of space, time, and gravity. The Hubble tension today feels very much like that old puzzle of Mercury's orbit. It is a persistent, well-measured anomaly that refuses to go away. And it is telling us in the quiet language of data that our current story of the cosmos, the standard model of cosmology, is not the final word. It is not that the model is wrong. It has been spectacularly successful in explaining so much about our universe, but it is likely incomplete. It may be just one chapter in a much larger, more complex book. This crisis, therefore, is an invitation. It is a call to a new generation of physicists and astronomers to look deeper, to question our assumptions, and to search for the new physics that lies beyond our current horizon. The universe is whispering a new secret, and the Hubble tension is the clue that tells us where to listen. We are not just waiting passively for this new physics to reveal itself. Humanity is actively building new eyes to look deeper into this cosmic mystery, to gather more precise data, and to hopefully, finally, resolve the Hubble tension. The next decade promises to be a golden age of cosmology, thanks to a new generation of powerful telescopes, both on the ground and in space. The European Space Agency's Euclid telescope, recently launched, is designed to create the largest and most accurate 3D map of the universe ever made. By precisely measuring the shapes and positions of billions of galaxies, it will study the history of cosmic expansion and the nature of dark energy and dark matter with unprecedented detail. Following that is NASA's Nancy Grace Roman Space Telescope. With a field of view 100 times wider than the Hubble Space Telescope, Roman will be a supernova hunting machine. It will discover and study thousands of type Ia Supernovae, dramatically improving the precision of our local measurement of the Hubble constant and helping to rule out any potential systematic errors in our current data. On the ground, massive new observatories like the Vera C. Rubin Observatory in Chile will survey the entire visible sky every few nights, creating a movie of the universe that will capture countless transient events and provide a torrent of new data. These new eyes on the cosmos are designed specifically to tackle the great questions raised by the Hubble tension. They will provide us with the clues we need to either find the subtle errors in our current measurements or, more excitingly, to confirm that a new physics is indeed required. The answer to this great cosmic puzzle may be within our reach. And so, we find ourselves in a remarkable moment in scientific history, a time of profound and beautiful uncertainty. It can be unsettling to learn that our best model of the universe has a crack in its foundation. But this uncertainty is not a weakness. It is the very engine of scientific progress and the source of its deepest beauty. A universe that was completely understood, a puzzle that was already solved, would be a static and uninteresting place. The existence of a mystery like the Hubble tension is a gift. It is a sign that there is still more to learn, more to discover, more wonder to be found. It reminds us that science is not a collection of unchanging facts written in a textbook. It is a dynamic, human process of questioning, exploring, and being willing to be wrong. It is the quiet humility to admit that we do not have all the answers, and the relentless curiosity to keep searching for them. The Hubble tension is a testament to how far we have come, a measure of our ability to make measurements so precise that we can detect a subtle disagreement between the beginning of time and the present day. And it is a promise of how far we have yet to go. It is in this space of not knowing, this beautiful and fertile ground of uncertainty, that the next great ideas will be born. Our journey through the cosmos has led us to a quiet crisis, a beautiful paradox. Imagine the universe as a grand symphony, one that has been playing for 13.8 billion years. For a long time, we thought we understood its score. The music from the beginning of time, the echoes of the Big Bang, told us the symphony should be playing at one tempo. But when we listen to the orchestra of the present day, the music of the nearby stars and galaxies, we hear a different tempo, a slightly faster rhythm. The two sections of the cosmic orchestra are out of tune. This dissonance is not a mistake. It is a message. It is the universe telling us that our understanding of its music is not yet complete. There is a deeper harmony, a more complex and beautiful score, waiting to be discovered, one that can reconcile the ancient past with the vibrant present. The Hubble tension is not a reason for anxiety, but a reason for wonder. It is an invitation to listen more closely, to look more deeply, and to appreciate that we are living in one of the most exciting moments in the history of science. A time when the very foundations of our cosmic story are being rewritten, and in that quiet, ongoing discovery, there is a profound and gentle peace.